Hello, I'm Dr. Ashton Robinson Cook. I'm a meteorologist at the National Oceanic and Atmospheric Administration Storm Prediction Center in Norman, Oklahoma. I also research U.S. tornado outbreaks, seasonal forecasting of severe storms, and long-range climate variability related to severe weather. I want to talk to you today about how the frequency and intensity of severe thunderstorms and tropical cyclones are projected to change in a changing climate. Detecting the influences of climate change on extreme weather is a very challenging task. Part of the challenge is attributed to the length and reliability of our records of historical weather extremes. Our severe weather reporting databases are considered reliable dating back to the 1950s for tornadoes, the 1970s for tropical cyclones, and the 1980s for hail. Each of these databases are associated with uncertainties because of underreporting before the rise of cell phones and social media, and a lack of many weather satellites before the 1970s for tropical cyclone detection. Despite these challenges, a couple of studies have indicated an observed shift in the number of tornadoes recently. These studies document that more tornadoes occur in clusters or outbreaks despite an overall decrease in the number of days with tornadoes in the U.S. Researchers suspect that this shift to larger outbreaks is tied to the changing climate over the past 30 to 40 years, and they're continuing to examine whether this trend will continue. Tropical cyclones, commonly called hurricanes in North America, also have exhibited a change in character. The Intergovernmental Panel on Climate Change states that an increase in tropical cyclone intensity has been observed since 1970. This increase is correlated to increasing sea surface temperatures during that time period. However, there is large disagreement between model projections of future tropical cyclone activity. Globally, models project a reduction in frequency but an increase in intensity of tropical cyclones. But there is no current consensus on how these changes affect an individual ocean basin, like the Atlantic. We also don't yet understand potential changes in the tracks of these systems. Imagine we have stronger tropical cyclones in the future, but they all have tracks that take them away from land. This situation would require very different management strategies than if tracks were projected to hit land more frequently. Assessing changes in severe thunderstorm and tropical cyclone behavior is quite challenging for multiple reasons. At this time, there is no way to verify these small-scale features in the output of global climate models, despite the range of scenarios they produce. Some models have inconsistent results from scenario to scenario because they are more, or less, sensitive to changes in greenhouse gas concentrations. Some models vary the behavior of the Northern Hemisphere jet stream, which represents a significant challenge because the jet stream plays such an important role in the development of U.S. severe thunderstorm and tornado outbreaks. Global climate models have very coarse spatial and temporal resolution by design. They are designed to capture large-scale behavior of the Earth's climate system and by themselves cannot resolve individual tornadoes, hail, or wind-producing thunderstorms, or even tropical cyclones. Researchers have addressed this design issue by identifying environments within the atmosphere that favor the development of these severe weather events. We assume that if the environments change in the future, the patterns of severe events will change accordingly. For hail and tornadoes, favorable environments generally revolve around ingredients called convective available potential energy, or CAPE, and vertical wind shear. Higher values of CAPE favor large hail and intense thunderstorms, and higher values of wind shear favor tornado development. Most of the current studies do not account for changes in lift, which is another key ingredient for severe weather outbreaks. Lift can be produced by small waves embedded in the upper-level jet stream or by convergence of winds along low-level jets, frontal boundaries, or other small-scale features. Many previous studies have projected increases in CAPE using future climate simulations. Researchers have related this change to a potential increase in severe thunderstorm development, although these studies have yet to account for the various sources of lift or for factors that may inhibit severe thunderstorm initiation. We are also presented with an additional challenge. While wind shear and instability are necessary conditions for severe convection, the presence of both in a particular region does not guarantee that hail or tornadoes will occur. Instead of using global climate models, some scientists have used dynamical downscaling to study how extreme events might change in the future. The benefit of dynamical downscaling is that many of the weather phenomena that produce severe weather, like tropical cyclones and supercell thunderstorms, can be resolved in these high-resolution models. This approach has shown promise and represents an emerging area of research. As you can see, it's an exciting time for researchers like me. We are committed to making progress to help decision-makers plan for these extreme events.